Hello everyone. Today we discuss contest about dynamic programming. It was harder than usual, so I kind of expect it to be hard, but not that hard. So the problem is again that the even easiest problems about dynamic programming on code forces are quite difficult. So if you like go here, problem set and pick the DP. So there are problems, like let's sort by difficulty here. So there are problems with difficulties like 800, but if you read these problems, they're not actually about DP. So they probably can be solved using DP, but they usually can be solved without DP using some, say, either greedy solutions or some brute force, something like this. So not really about dynamic programming. So if you want to have actually dynamic program problems, you go much deeper. So you go to something here. So this is probably closer to the to DP. So like again, I read this problem. I remember it. So I was trying to get something easier, but all these problems here are just not dynamic programming. They like dynamic programming may help you to solve these problems, but you actually don't need it that much. So that's the reason why the contest is so difficult today. I probably should have just reduced number of problems, because to make contest as like kind of the same difficulties before, I probably could just remove these 2 problems, and these 6 problem will have kind of appropriate difficulty. Problem G is actually not that hard. Problem G is actually not that hard if you know what you're doing. Problem H is how much am I spend on problem H? Let me see. So I started 21. Okay, it's almost an hour solving this problem. It was all not because the problem is difficult itself. Problem itself is not that difficult, but because you need to restore the certificate. We'll talk about it because it's mostly technical difficulties, but there's just a lot of code in this problem. I also spent a lot of time solving problem C for some reason. For problem C was my kryptonite today. So it looks easy. It should be solved something easy solution, but I tried to do it with some very strange way and spent too much time solving it. Okay, so let's go. I will not show you my recording. My recording is it's like more than 2 hours long, and most of the time I'm just thinking or trying to debug all this stuff. So yeah, it's not very interesting to watch. So instead we will just I will just show you my code and discuss all the problems on the whiteboard. Yeah. So let's go. First 2 problems kind of very similar actually. So what we need to do, we have array and we need to pick 3 elements. So here you need to pick 3 elements, and in the next problem you also need to pick 3 elements. And you want to do something then. So in this problem you want to pick 3 elements such that parameter s is increasing and sum of parameter c, total cost, is minimal possible. Okay, so the idea of problems A and B is kind of the same. So what we do is basically do something like this. So imagine you have your array, yeah. So you need to pick 3 elements like 1, 2, and 3, like I, J, and K. Yeah. Easiest way to think about it is to make like 2-dimensional structure. So imagine you have 3 copies of your array, like 1, 2, and 3. Yeah? And you pick first element in the first copy, I, second element in the second copy, and third element in the third copy. Yeah. And now you kind of need to do the following. You need to pick some element here, then go down somewhere here, and then go down somewhere here. Okay. Okay, at least for me, it's much easier to understand it like this. Then you there are 2 ways now. You can either create array like 3 by n, so like d array 3 by n, and like this, yeah. 2-dimensional array. Or you can create 3 different arrays, like you suggest. Yes, you can create d1, d2, and d3. Yeah. So in array d1, you get all optimal sequences of size 1, so you pick 1 optimal element. In array d2, you pick one element here and optimal element from this array. And in the third array, you pick element here and some sequence of two elements from here. Yeah? So let me show you how. Okay, this code is not perfect. Okay, probably should do it more clear, but okay. So what I'm doing here, I have two arrays, not three, because like first array is just array C. Yeah. So again, let me show. Let's put it here. This here. So first array is just array C in this configuration. Yeah, because first array is just minimal cost of one element. So cost of one element is just Ci. Yeah. So I pick one element with with minimal cost is just element Ci. So this array is array D, not good naming, and this array is D2. Okay, it is the first problem. I try to solve it as fast as possible. So that's my naming is not great. Yeah. Okay, so we go left to right and just calculate these arrays. Yeah. So in array D, in the second row, first array is just equals to C. Yeah. Why it's equal to E? Okay. Why it's equal to this? That's strange thing. That's a trick I learned some time ago. So basically, I want to put some like plus infinity here. So I want to initialize. I'm looking for minimums. Yeah. So I need to initialize minimum of something large. Yeah. But if you put int max here, then if you add something to this int max, you get integer overflow. So instead of, actually, I won't have integer overflow because I have 64 bits. Yeah. So you need to find long max like this. Long max. It will make more sense. Yeah. Like this. So basically, if you put maximal possible element as your initial value for minimums, and you accidentally add a little, you get integer overflow and everything goes, yeah, everything goes wrong. Yeah. So that's the way to put large element without possible overflow problems. Yeah. Again, I put it in 4 positions. Again, not great. You probably need to put some constant. You put some constant inf equals something like this, and here we just reuse it. This something like this probably would be much better than my code. Yep. Something like this. Again, what this code does, I go left to right and calculate both these arrays D and D. You can do it in 2 steps. You can calculate array D and then calculate array D2. So you can calculate this array row by row like this, like row, yeah. Or you can calculate it column by column like I do, like this. Doesn't matter that much in this problem. Do whatever you like. So I go column by column. Yeah. So I calculate every time I calculate all 3 elements here. Okay. First element I don't need to calculate. I know its cost. Second element here, I choose what is the previous element. What is this element? Okay, they have different namings. Let me change naming here. So this I, so this will be J. Yeah. Let's erase this so it will not distract you. Yeah. So I pick this element. Now I want to find optimal sequence of 2 elements. Yeah. So I look what is the previous element here, J. I check that this element should be less than mine and calculate minimum. Yes, it's my cost plus its cost. Okay. Now array D contains optimal sequence of 2 elements. Okay. Now I just do the same for the third element. For the third element here again, so this is I, this is J. Yeah. So I look what is the previous element. Now for this previous element, I know this optimal sequence. It's just D of J. Yeah. So I take this sum. Yeah, it's here. Yeah. Add one more element here and have the so this is the sum of all 3 elements. Yeah. So it's last element plus 2 previous elements. Yeah. Out of all possible choices, take the minimal one. Let's see, just calculate result is optimal. It's minimum for all of this. Yeah. Not a great code, actually. Let's look. Maybe someone have better code than me. Yeah. Who is the fastest today? Okay, fast code. Fast code is not usually the best one, but anyway, let's see. Pretty much the same. Okay. K, what is K is just 3, yes? Yes, okay. Okay, you have not 3 different array, you have one array 3 by n, or n by 3 in your case. Yeah. No, 3 by n. So strange name. Okay. You have array, not vector. Okay. Okay, that's problem A. Okay. Problem B is very similar actually. We again need to pick 3 elements. Now we can pick the same element because we have not less but less or equal here. Yeah. So we need to pick 3 elements. Each next element is greater or equal than the previous one. So we can pick 2 same element multiple times. Yeah. And we multiply them, first element by p, second by q, third by r. And calculate maximum sum. So instead of minimum, now we have maximum. So idea is kind of the same. So we replace minimum with maximum. We have different costs. So before we had just sum of cost. Here we multiply cost by this p, q, and r. But overall, it is the same problem, almost. Yeah. So let's look at the difference. Okay, so this time I decide I will implement it a little bit more clear. Again we have it is infinity, yeah. So it's long divided by 2. So infinity to avoid overflow problems. Yeah. Again, I create 3 arrays. Yeah. First array is just cost multiplied by p. Second array is something of size 1 plus cost multiplied by q, and it's something from array 2 plus r multiplied by a. Here again, difference from this problem is I don't need this second 4 actually. This second loop I needed it before because I need this property. Yeah, so I need only previous elements which are less than me. And here I need all previous elements, so I just calculate the optimum prefix. Okay. So d1 will be maximum on the prefix for a single element. D2 is maximum on the prefix to pick 2 elements. D3 is maximum on the prefix to pick 3 elements. Yeah. So I output d3 of n is just maximal optimal way to pick 3 elements on a prefix of size n. Prefix of size n is just all elements. Do you see already? So it's the easiest DP problems I found in code forces. For some reason they didn't use easier problems. I believe you can create easier problems about dynamic programming, but for some reason it's not that popular. Let's read some on. Let's read. Okay, pretty much the same. Yes. DPP, DPQ. Why not? You don't need third array, you just calculate maximum. Okay, makes sense. Okay, so that's problem A and B. Any questions? No? Okay, let's move to something more interesting. Problem C. I hate problem C with all my heart, actually. So what we have in problem C? We have a string. We need to replace some commands. We can replace T to F or F to T. And we want to maximize distance from the origin. So what's happening? We have some program. Let's say some F T F T F F F something like this, t. Yeah. So what we do, we start in position 0 and just facing right, and just apply all these commands one by one. So we go forward, forward, then we turn, and again go forward, and again turn, and give forward again, and 4 times go forward, 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 and then again return. So every time we see T, we change the direction, here, here, and here. And every command F is just move forward one position. I believe it can be solved with something very simple, greedy approach, probably. What was my plan? So I finally using dynamic programming, so I solve it like this. No, again, it's kind of standard way to solve these problems, but for some reason it was difficult for me. So what I want to do, I wanna, so imagine I already processed some prefix. So I processed some prefix of size I. In this prefix of size I changed j elements. Okay, let me read my code. Maybe I used other. No, this is the code. I change j elements, and by ending, so what will happen when I finish this? So if you read first I comments and change j comments, then by the end of this prefix of size I, you will have some position. Yeah, your position is basically your coordinate plus your direction. Yeah. So what I'm doing, I remember for each triple of size of prefix. Okay, so let's see. So I is size of prefix. Size of prefix. J is number of changes. Number of changes. And E in my case, yeah, it's direction. Yeah. So for each triple like this, I remember what will be maximal coordinate. So that D, E, I, J in my case. So it will be max coordinate. Max coordinate. Okay, at some point I actually read that you need not maximal coordinate, but you need maximal distance. So it's possible to get negative coordinate. So if you go, you can go right, then turn, and then go far, far, far left, and go minus x. And you want to maximize not the coordinate, but the distance. And I solved this problem by just reversing the starting point. So if the optimal answer is to move somewhere here, instead of finding minimum and maximum, you can find minimum and maximum in two different arrays. Also possible. I cheated. I decided I will just reverse the whole path. I will start the path from the left. It's minus x. So it will end in position plus x. Yeah. So I alternate not the final sign of the coordinate, but the initial direction. Yeah. And now in both cases, I look for maximum. Yeah. So again, the trick is basically instead of looking for minimum, I look for maximum of negative value. That's the trick. Okay, and just now we just need to extend sequence by one. Yeah. So you already processed some prefix. You have one more character here. Yeah. So you look at this character, and depending on which operations you have, you see if you change it, what will happen, if you don't change, what will happen, and you move to some new state. So it's dynamic programming moving forward. Yeah. So I have my current state. I look what action I'm doing now and move to some next state. Okay, so that's how I implemented it. Let's see. So I look at all my states. So I mark initial state. My initial state, I'm standing in point. So I processed empty prefix. So prefix of size 0, made no changes. Yeah, I'm direction may be either 0 or 1. In both cases, I'm standing in point 0. Yeah, so that's the initial state. So from here, I start my process, right? Now, how do I change my current state? So I'm looking at my current state here. So if it's int minimum, is not, it means it's just not approachable. So this state is just not usable. So I cannot go to this state probably. So I just skip it. Now I look at my current character. So if my current character is f, and I always have two options. I can either keep this character or I can change it. Yes. If I keep the character, I do this. So if I keep the character, I move to the state with the same direction, process one more character of my prefix, and have the same number of changes. Yeah. So that's my new state. So I go to this next state and update the value. Yeah. So it's called relaxation and all this here, it doesn't matter. So I go to this state and update this value by applying maximum. We're looking for maximum, yes. So look maximum of the previous value and the new value. New value will look like this. So this is just plus minus 1 depending on direction. Yeah. Okay. So again, the idea, again, so if you're not that familiar with dynamic programming, the idea I'm using here is sometimes, okay, so what's happening sometimes? You have your current state and you look at the previous states, yeah? So you look at the previous states, find something like maximum here, and write it down here. So every time you look at dynamic programming, you look at your current position and see, how can I get to this position? So you look at the previous state, how did you get to this position? Usually, it's actually much easier to think other way. So you look at your current state, you already know this value, yeah, and you apply the next step. You see what will happen if I make one more step. So if I make one more step, I will move to these states, yeah. So you move this step forward and update these values, yeah. So just different direction of updates. You basically do the same updates actually, but in different order. It's much easier to track. Yeah. So what I'm doing here, so I'm standing currently in state. So my current state, this state. I have only two updates. What? So my current state is like EIJ, yeah. And if I have letter F and I don't change it, then my new state will be E, direction is the same, I plus 1 and J, yeah. See, so this I update this next state. Okay, if I change it, so if I change F with T, then I move to another state, yeah? So I move to a state with different direction, yeah? And I make one more change here, you see? So J plus 1, J is number of changes. So I make one more change, I move to different direction, and my coordinate will be the same. Okay, so here, so that's how you process one more step. So you read one more letter, you check either you keep it or you change it, and depending on what you do, you make one of these two transitions. This part is actually the same. I believe I could simplify this code. This part is the same, but when you have letter T. If you have letter T, if you keep it, you do this, the same as this. If you change it, you do this, the same as this. Okay, also in the end, you can change the same character multiple times, but you need to do it exactly k times. I hate this problem so much. Why do you use it? So you need to change exactly n letters, but you can change the same comment multiple times. That means that you can, so in the end, you can just change the same letter back and forth, Yeah. So if your number is changed have the same parity, it's also fine. So I check all final states with the same parity of number of changes. Yes, and find maximum of all possible final states. So here I check all possible final states. Sometimes in dynamic programming you have multiple final states. So here I just look at all possible final states and find the maximum of them. Okay. Okay, this problem, see, actually, now I'm looking at it, the code is not that difficult, actually. I don't know why I spend so much time on it. Maybe because I'm just tired today. Okay, I don't know. Sometimes problem is not. Sometimes you look at the problem, think it should be easier. So you kind of want to simplify the code. You want to cheat a little bit. Here, the best way to solve this problem is actually just to write normal dynamic programming without any cheats. If you try to cheat, you will get some strange mistakes. Let's look at Alexis code, for example. Oh, that's more code than I have. Okay. Okay, probably doing kind of the same as me. So okay, that's kind of direction. Okay, so its direction is 0, you're moving forward or backwards. Yeah. Ah, that's because you calculate both maximum and minimum. Okay. That's why you need to twice more code to track both maximums and minimums. Okay. Again, I cheated by reversing the whole sequence. So if you not the sequence, reversing the mirroring the path. Yeah. So I initially go not to the right but to the left. So if the final position is in the left, I will mirror everything and it reflect everything. Yeah. And it will be in the right. Yeah. Okay. Any more questions? No. Okay, let's go problem D. Problem D is actually much easier, at least for me. I don't know. Problem D looks like easy classical dynamic programming problem. So what we do in this problem, we have a sequence. So basically we have, okay, let's formalize. We have two elements. We have two types of elements. So we have N1 elements, let's say, of type 1, and I have N2 elements of type 2. And if you have any sequence of type 1, the length of this sequence should be at most k1. And if you have sequence of elements 2, length of the sequence should be at most k2. Yeah. What we just need count number of different good sequences. And all constraints are very small, so you don't care at all. You can write it any possible dynamic programming will work, I believe. How I do it? So I go from left to right and just build the sequence. How I build the sequence? I put some number of ones, then some number of twos, then again some number of ones, then some number of twos, and so on. Yeah. So I stop here. So I put elements with the whole segments. So I put every time I put segment of equal elements. I put some number of elements 1, number of elements 2, some number of elements 1, and so. Yeah. Now, how to? So what I need to remember? I need to remember total number of elements equal 1 and total number of elements equal 2. Yeah. So here I have 4 plus, so I have 8 elements equal 1 and like 5 elements equal 2. Yeah. So in D8, 5, yeah, I will have this state. So again, D of ij will be equal number of ways to build sequence when you have I elements of the first type and j elements of the second type. And then to extend this sequence, I just need to know the final element here. So if the final element is 2, I can add some segment of 1s. If the final element is 1, I can add some segment of 2s. Yeah. Okay. So let's read the code. Let's see. That's it. Very, very short code actually. So I use 2 arrays here. You can make one 3-dimensional array. I use 2 2-dimensional arrays. Up to you. So because I need 2 arrays, I kind of duplicate this code. You see, it's kind of doing the same thing. Sometimes I do it like this, sometimes I would use three-dimensional array, depending on problem. Here I decided it would be easier to make two-dimensional arrays. Okay, so again, I do forward dynamic programming. So I look at the current state and propagate this data to the next state. Yeah. So I take the current state, starting from some, you need some base of dynamic programming. So I start from state 0, 0. State 0, 0, I didn't put anything. Yeah. And I have one way to do it. Okay. I put it in both di and d2 because I don't know which element is first. Yeah. So dy means first element is 1, d2 means first element is 2. Okay. Now I look at all states and propagate it to the next state. So how I do it? I create a new segment. Length of the segment will be from 1 to k. Yeah. So this is my new number of elements. If it is in a given limit, then I update the new state. Okay. Here we don't calculate maximum or minimum, we calculate sum. It's actually much easier usually. Yeah. So so I take the next state, add my number of ways to do it. Yeah. And calculate model. Okay, just okay. This part kind of standard. Here is the same thing, but in reverse for the second type of elements. Yeah. That's it. So some of this stuff will be the result. Any questions about this problem? Okay, I think it's much more standard dynamic programming problem than the previous one actually. So if you solve problem C but not problem D, it's kind of strange. So try to solve it. Again, it should be this. Let's look. Again, let's read some of your solutions. Seven. Different, not this problem. Okay, you did it in different ways. So you okay. So you count number of elements you used and length of the last sequence, I believe. And you have two of them because you can. One of them is always 0, right? Okay, even this is 0 or that is 0. Okay, so one of these two elements is actually always 0. Okay, why not? So every time you add one more element, and you either extend your current sequence or not extend your current sequence. Why not? Nice code. Again, if you have small constraints, you don't care that much. You can do it whatever. So this code has better time complexity, but it doesn't matter. Okay, let's move next. Problem E, also nice problem actually. Difficult, but nice. Again, the idea is that you can restore this sequence going left to right. Again, why this problem can be solved using dynamic programming? How can you find? So in this context, I just told you all the problems I know about dynamic programming. If you don't know, how can you see that the problem can be solved using dynamic programming? Well, because if you look at this sequence, and you already restored some prefix, yeah, and you think what you need to put here, you only care about last few elements. So if you know, for example, here you have 1, here you have mine, yeah. Then you already know what will happen here, right? So this position will be either, so it will be either another mine, or it may be 1, yeah, then you don't have mine here. Or it may be 2, then you need to have mine here. Or it cannot be 0 because you already have mine, yeah. So you just know, you just need to know on some last element of your current prefix. Yeah, so for every prefix, you don't need to have any information about this part. So these elements are just not interesting. You're only interested about some few last element of the sequence. Okay. Well, let's actually look at all. Let's look at all these cases actually. So I have two elements. Which options do I have? I can have bomb and bomb. So I have bomb and bomb. Then here, what I can do here? I can have either another bomb, or I can have one, or I can have two. No zeros. Yeah. If you have bomb and zero, not possible. Yeah. Bomb and one. Yeah. Then here you have either zero or one, not two. Yeah. There's two options here. You have three options. If you have bomb and two, then you have only bomb here, only one option here. Okay. Already have half of options actually here. So if this is not bomb, if it's something like zero, doesn't matter what, or one, doesn't matter. And then you okay. So let's not simplify. You have zero and then one. Then here you must have bomb. Yeah. If you have zero and then two, impossible. Shouldn't matter. If you have zero and bomb, shouldn't happen. If you have zero and zero, then you have here either zero or one or two, not bomb. Not two, zero or one. Okay, so you can just write down all possible situations you may have. Now, what I did actually, I simplified the problem. So I see that some cases are actually similar. So for example, this case is similar to this case. See? And this case, it's another color. And this case is actually similar to this case. Yeah. So we have case when we have these three options. We have case when we have 0 or 1. We have case when we have only bomb. Yeah. No, because we either have 1 here and no bomb here. Or if we have 2 here, then we must put a bomb here. Yeah. So actually we have only 3 options here. We have options following. So imagine we already filled some prefix. We have the following options. We either have bomb here, mine. We either have mine here, yeah. Then it doesn't matter what will happen here. This option 1 should be 6 cases. There's actually 3 cases. So there are 6 of them, but some of them are just the same. Are just 3 cases actually. Second case, when we have not mine here, not mine, and we cannot put mine here. So it's either we have 0, or if we have or if we have 1 and mine here. Yeah. Basically, situation where we have no mine. It's no mine here. Yeah. So here we can put either 0 or 1. And the third case is when we forced to put a mine here. Now, because we either have 1 and no mine here, no, then we're forced to put mine here. Okay, let's put 0 here. So put 0, or we have 1 and 1. Also, we're forced to put mine here. Or if we have 2 and mine here, also we're forced to put a mine here. Okay, so these 2 cases are the same, these 3 cases are the same. So I will calculate 3 values for each of these 3 cases. Okay. Okay, I have strange number. So dB is B from bomb. It's not. It's mine, not bomb. So this case is called dB in this case. dB. This case is called D0 because I have no mine. and it's d mine because I forced to set a mine. Okay, I initialize both d0 and d1 because I don't know if the first position is mine or not. Yeah. So these two cases kind of set the first element of the sequence. So it may be mine or not mine. So I initialized all of them. Now I go left to right and try to, again, propagate forward my dynamic programming. Yeah. So I look at the current character, check what I can put in this position. I have 4 options. Yeah. I check if it is possible to put this character. So if position is not a question mark and not the same, I just skip it because this position is fixed and it's not this. So I can't put this character into this position. And now I just track all these 4 cases one by one. So if I put a new mine, no, I can put it either here or here. See? In both cases, I go to position dB. So I go either from d1 or from dB to position dB. Okay. Well, let me split it into 2 just to make poop, 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 poop. To simplify. Okay. Again, okay, here are 2 options. I can put mine here, I can put mine here. So I take d1 value, I take dB value, and propagate it to the next dB value. Because dB means I put a bomb. Mine doesn't matter. Yeah. If I put character 0, how can I put character 0? Well, let's see. I can put character 0 actually only in one case. Here I can't put 0 because I have mine here. Here I can't put 0. I forced to put mine here. So I can put 0 only here. Yeah. If I put 0 here, it means I had first state d0, and after this 0, I also have state d0. Yeah. So it's transition from d0 to d0. If I put 1, I can put 1 either here or here. If I put it here, then here is no bomb. Yeah. If I put it here, then here must be a bomb. Yeah. So I have transition from d0 to dB. Here, no. To d1. D1 forced bomb again. From either from d0 to d1 or from dB to d0. Here. Okay. And finally, if I have 2, it's only possible if I have bomb before, and now I forced to another bomb. So it's transition from dB to d1. Again, just carefully write, take a piece of paper, write down all the transitions. Yeah, try to simplify it to have smaller number of transitions, and then just carefully implement them one by one. That's how I usually approach problems like this. Just carefully just take all the transitions and just draw some picture so to make it easier for you, and then just implement them one by one carefully. No rocket science, actually. Just careful implementation. That's it as problem E. Do you have easier solution than mine? Let's look at your solutions once again. Yeah, I believe you're kind of doing the same thing. Here you have, okay, you have 5 values. Okay, so you have not 3 states, you have 5 states. Some of them should be the same then. Yeah, this state and this state look the same, absolutely. Yeah. So these values are always the same, you see. and these values are always the same. But it's okay. You just calculated the same value multiple times. You call it in different cases. So if it is 0, if it is 1, it's not the same. Not the same. But still, again, it can be simplified to 3 cases instead. Yeah. Okay, this was problem E. Very nice problem, actually. So not that much implementation details, but it's a nice dynamic program problem. Whew. No, okay, let's go problem F. Problem F is also kind of solvable, but difficult. Actually, for me, problem G was even easier than problem F, actually, but problem F is also easy. So what we have in problem F, let me show you. Again, it's the problem statement itself is very confusing. So again, so what are they doing? So they have some sequence. Then they apply some number of local swaps. So you swap neighboring elements at most s times. Yeah. After that, after all these swaps, they look at the first k elements and want to minimize the sum of these qualities for them. Yes. Sum of what? Sum of something. It's called from strange log quantity, whatever it means. Yeah. Again, it's a lot of misdirection happening in this problem statement. Yeah. So they wanna make you think in this order. So first we apply some swaps, then we pick first k elements and wanna minimize. If you think in this order, it kind of makes very strange impression of what's going on. Let's just reverse all the thinking. So imagine we know which elements should be in first position. So I want to put some k elements in the first positions. So I have some elements here. So imagine I fixed these elements. I don't care about these elements. Yeah? So imagine I know which 5 elements I want to put in the first 5 positions. Then in the initial array, these elements are somewhere here. Yeah? I need to put them in first 5 positions. And I want to do it using minimal number of swaps. Yeah? So if I can put them here with no more than s swaps, then it's a valid answer. Yeah. So if I can put these k elements into first k positions using at most s swaps, then it's possible. Then these k elements may be in the first k positions in the end, and then I just count minimal sum for all valid positions. Yeah. Okay. Now, so imagine you pick some elements with positions, I say x1, x2, x3, x4, and x5. How many swaps do you need to put these elements to positions 1, 2, 3, 4, and 5? No, it's actually quite easy to calculate. Yeah. So we need to put first element to position 1. To do this, we need x1 minus 1 swaps. Yeah, to just swap this element here, 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 here. Yeah. Now we take second element. We didn't move it yet, so it's still in this position. And we need to put it to the second position. So it will be plus x2 minus 2. And so on. The third element must be put to the third position. So it's plus x3 minus 3. Plus and so on. So this sum, okay, let's sum xi minus I should be not greater than s. Why this is important observation? Because we split the interesting function into sum of some independent values. You see? So before we need to put these 5 elements to these 5 positions. Yeah? And now we split it. We need to put first element to first position, second element to second position, and we can do it kind of independently. Yeah. So we can kind of independently pick the first element, then pick the second element, pick the third element, and so on. Basically the same like we did in the first 2 problems. Yeah. But in the first problems, we need to pick exactly 3 elements. Here we need to pick k elements. But the idea is the same. Yeah. So imagine you have array like again k by n. Yeah. So you pick the first element here, then second element here. The same way like we did in the first problem, but in the first problem we had 3 elements to pick. Here we have k elements to pick, but the idea is the same. Okay. Another difference is that we also need to kind of keep track of 2 values. So we need to keep track of number of swaps, this number of swaps. And we need to keep track of the sums of q's. Because we want to minimize the sum. And the idea is to put one of these values as another dimension of your dynamic programming. So we pick the thing which is smaller. So this is actually, this thing is kind of small. So this thing is not greater than n squared. Yeah. So I will use this value as another index in my dynamic programming array. Yeah. So in the end, what we'll have? We'll have the following dynamic programming. Let me write it. So we have array. So how the process of building the answer looks like. I go from left to right. Every element I either pick or skip. Yeah. And I need to remember the prefix I'm already get. So I pick the first sum element. On this prefix, so I have the same indices like in my program. Let me what is I, J, T? Okay, so I don't look at don't look there yet. Okay, don't spoil yourself. So you already processed prefix of size 1, I. In this prefix, you already picked some j elements. Yeah, and for these picked elements, sum of x, let's have another parameter, x t minus t. Yeah, like let's say numbers. Let's just rename it. Number of swaps equal to t. Yeah. So I have 3 parameters: I, j, and t. Okay. Now we just need to extend this state by 1. So I take a look at the next element, this element. I either skip it or I take it. So if I skip it element, skip, then I have state I, j, t. I move to state when I have I plus 1 elements, and still I didn't change this, so I have j and t. Yeah. Or you can take the element. If you take it, then again you processed again. So you process this element, you picked one more element, yes, and the total number of swaps will be t, its previous number of swaps, plus new number of swaps. So you need to pick this element and put it to position j, yes, because you pick j elements. So it will be plus I minus j. Yeah. Okay. And you process these 2 transitions and again recalculate dynamic programming. Is it clear enough? Okay, we move to difficult problem actually. What I did in this problem actually, to make it even more tricky, I use two-dimensional array instead of three-dimensional array. I use the same trick like in knapsack problem. So I reuse the same array here. So instead of having I, so I remove the parameter I here. But because I always move from state I to I plus one. So you can do it like this. Sometimes people do it like this. So you have state I, yeah, and you calculate state I plus one. Yeah. So you remember these values, you process them, process all the transitions, calculate new layer. And then you forget about this layer, calculate new layer. Yeah. So you remember only one layer of dynamic programming. Here you can do it even more easy because you can reuse the same layer, basically. So I will use the same array for both my current layer and the next layer. Sorry, it's just to make things more fun, just to show you how it can be done. So again, how we do it? So I use the same array. So this array D will work for both I and I plus one. Yeah. So this parameter I. So I move from layer I to layer I plus one, applying these transitions. Here, these two transitions. Yeah. And I apply these transitions on the same array because I can. Okay. To do this, you need to iterate right to left because you apply your okay. It's much easier to do it on the knapsack problem. So what's happening here? So I have transitions, but all the transitions go left to right by J. Yeah? So parameter J is always increasing. See? So I will go right to left. So every time here I have new values, and here I have old values. Okay? I pick this old state, apply the transitions, and update these new values. See? So by the end of this process, all values are new. Sorry for making solution even more tricky than it is. But again, that's why I did this, because I was afraid of having memory limit problems. If you carefully calculate, I have already array. So k is up to 150, and this parameter s. So okay, but you don't need billion. Number of swaps is like n square. So you already have an array like n cube. And if you make three-dimensional, you have parameter n power 4. Looks very okay. So okay, it's not 150 actually. So maximal value of s is actually when k equals to n over 2. So I don't know what's the maximal size of this, but the size of this array is kind of scary, and have 250 because its memory limits is small. So that's so it's not like I'm flexing here. I'm kind of flexing, but it kind of makes sense to decrease amount of memory here. Yeah, because of the time limits are okay, time limit is okay, but memory limits is scary. I believe so. So if you look at my let's look at my submissions problem F. 300 kilobytes. Really? That's much less than I expect, actually. Okay, so I'm very far from memory limit here. So probably I overcomplicate things. Probably I just overcomplicate things. Okay. Okay. Okay, normally I would do it like this. Let's say vector d of size n plus 1, then k plus 1. something like this. So you make three-dimensional vector, yeah, and you have d0, 0, 0 here, and here you move from I to I plus 1. Like this. That's more classical way to do it. Okay, so you move from state ijt to either state I. Okay, now you need two transitions. So you need transition d I j I plus 1. J t equals d. Okay, let's do it minimum maximum to make it more clear. Something like this, yeah. So you have two transitions. One transition when you skip the element, another transition when you take the element. Yes, you only take the element if number of swaps is not greater than s. If you do it, then you go to this state, you update this state plus this number. Okay, but you don't need this third dimension again. You don't need this third dimension. You can do the same in two-dimensional ring. Like this. Again, if you're interested in this trick, learn how to solve knapsack problem. So knapsack problem can normally solve in one-dimensional ring if you don't need to restore the standard matter. So not all variations. Okay, some variations of knapsack problem can be solved in one-dimensional ring. Let's say like this. Okay, we're left with two most difficult problems today. So okay, let's go. Let's just discuss them. Problem G is actually not that difficult. Let me show my code. So it's actually very short. So that's it. That's the whole code. If you know what you're doing, okay, I also have. It's just modular arithmetics. So if you know what you're doing, actually not that difficult. It's some mathematical. So I have some combinatorics here, but overall it's not. It looks very scary. Because you need to calculate again. It's some combinatorics involved. You need to calculate number of sets of m distinct intervals. You have parameter m, which is not needed. Yeah. M is not used anywhere else, you see. So just number of sets of intervals such that it's possible, so maximal number of non-intersecting intervals equal to k. That's what's written here. So I need to count number of ways to construct a set of intervals in such a way that the maximal number of intervals I can pick, non-intersecting intervals, is equal to k. Very scary looking. How do I approach problems like this? No, you need to think about the object they want you to construct. Yes. So they want you to construct very specific object. Yeah. So when you construct a set of intervals with some parameter, you see, this parameter is maximal number of non-intersecting intervals. So first thing you can think about is, how do I actually count this function f? Sometimes it helps. Yeah. So if someone asks you, what is the maximal number of non-intersecting intervals? How do you calculate it? No, you can calculate it either with dynamic programming or greedily. Yeah. Let's talk about greedy approach. So greedy approach works like this. So you have some intervals. You sort them by the right border. Yeah. And every time you pick the segment with the leftmost possible right border. Yeah. So you took all your segments. Let's pick the one with the leftmost possible right border. Segment, let's like this. So this right border is leftmost possible. Now you pick the next segment. So you pick the segment which do not intersect your segment. So you skip all segments like this. So skip. And then pick the segment which do not intersect your segment with minimal like this. So this we take. Yeah. And every time you have some current right border, you need to skip all the segments. Again, some segment like this, you have segment like this. So again, you skip all this and pick the segment which do not intersect. So like this. Let's make it shorter. So again, how to greedily find maximal number of non-intersecting segments? You sort them by the right border. Okay, these are not sorted. Okay, let's sort them. Boom, boom. You sort them by the right border and look at them one by one. So if the segment doesn't intersect the previous segment, then you can take it. If it intersects, you just skip it. Okay. So this is how you calculate the parameter k. So you count just number of segments you picked. Why it's cool to think about it? Because it kind of gives you the intuition of how this object should be constructed. Now, imagine you go in other direction. So you need to construct some set of segments with some parameter k equals, I don't know, 3. So how you construct some segments? So let's construct them again in increasing order by the right border. So you take the first segment, it is somewhere here. Yeah. Now you take the second segment, it is somewhere here. Between them, you can put any segments which intersect this segment. So you can put anything here, anything which intersect here. Okay, I'll just draw the same pictures before. Again, so instead of calculating function, you think, okay, if I have the function, how I build the object of this function. Okay, and you can build it like this. You put one segment, you put the next segment, do not intersect this segment, and something in the middle which you skip. Yeah? And then put the third segment, which do not intersect this segment, and again something here that you will skip. And something in the end you will also skip. Okay, so you think about how would I construct the object that I need to count. Okay, now we need to do some dynamic programming. Yeah, so what we'll do, I will split this process into steps. So step is here it's very intuitively. So it's natural to pick step when you pick every segment. So I put the first segment here. All I need to remember is actually this position. Yeah, I don't need to know anything about so this left border is not important. Only right border is important. Yeah. Now I will put the next segment here, such that it do not intersect this position, and pick the right border here. Let's write another picture. So imagine you already put some segments here, and you know the right border of the last of them. Let's add another segment. So we need another segment which do not intersect this. So it must be somewhere here. Yeah. And we need to remember this position. So this position I, let's say this position J. Okay. Now this left border of the segment can be anywhere here. Yeah. So we have some number of options. And we can add some segments which will skip. Yeah. Segments will skip. They look like this. The left border is somewhere here. Right border is somewhere here. We can count how many possible segments there are easily. Yeah. So left border is anywhere here. Right border is anywhere here. I just count number of possible left borders, possible right borders, multiply them, and I have total number of possible segments. Okay. Whew, difficult problems. Okay, let's read. Very short code actually. What I'm doing. Here I'm pre-calculating powers of 2. I need powers of 2 because here, yes, you see. So you can add any subset of these intersecting segments. So I know how many segments I have. So I can add any subset of this set. So it's 2 power number of elements in the set. So this is why I'm pre-calculating powers of 2 here. And that's just dynamic programming. That's it. Very, very short. Let's go. So I go left to right. And I also need to remember how many segments you have. Yes. I go left to right. So I is my current point. Okay. And how many segments I already picked. Then I want to pick one more segment. Yeah. So I choose the right border of this new segment. See? Now, X is number of okay, so this is number of segments I can skip. Yeah. So this left border has I positions. This right border have j minus I positions. Yeah. So all the segments with left border here, right border here will intersect this part. I will skip them. Yeah. So there are that many skippable segments. I can pick any subset of them. So it's 2 power this possible ways to pick these skippable segments. And now I need to pick a segment with this position. I can pick not one segment, but many of them actually. So you can take several of them. So you can see how many possible segments there are with this right border, and pick any non-empty subset of these segments. Yeah. So I have j minus I possible non-intersecting segments. Yeah. And I have 2 power this minus 1. This strange way to find mass because of modular arithmetics. That's number of ways to pick some non-empty subset of elements with this right border. And just make this transition. So this is my transition. So I move from state it to state g t plus 1. T is number of segments I picked. Yeah. So it was t, now it's t plus 1. Now in the end, after the last segment, I also can add some number of skippable segments. So in the end, I pick the last segment multiplied by number of skippable segments in the end after the last segment, and calculate this total sum. Scary problem. Combinatorial. We have some plus some strange dynamic programming. Difficult problem, but doable. You see, nothing that impossible here. So all actions are kind of so again, the idea is that you look at the process, how you construct the object. So you need to study your object you're working with. Yes. So you look at your object, you need to count and think, okay, how would I construct this object step by step? Yeah. And then just look at these steps, make some how it's called, milestones. Yeah. So you move from one step to the next. So, and then for every state, you calculate, in this case, number of ways to go to this state. Sum over subs. Oh. Do you need, why do you need sum over subs? Okay, in some sense there is sum over subs. Yes, okay. Again, it's always tricky when problem statement includes some subsets. It's already look heavy. Yes, it's just by thinking about some sets of distinct intervals. So again, so like this definition is already hard to imagine. But you need to learn. So again, it's not it's not easy problem. It's difficult problem. But after you master dynamic programming, you definitely can solve problems like this. So if you solve more combinatorial problems, just learn how to deal with combinatorics. It's not that difficult after first 100 problems. Next 100 problems is much easier. Can you explain it again? Since the whole problem. Explain what? Did you miss some specific part or just the whole problem? Oh, themed for mathematical combinatorics. It's an interesting question. I don't know. Again, it would be very difficult. Maybe okay, it's good. I will try to find some easy combinatorical problems. It's a good. It's actually it would be good idea. Yes, maybe we need to find some easy combinatorical problems and train specifically combinatorical skills. Which part to explain? Just the whole part. It was like half an hour long explanation, so I don't know. So start from the beginning or which? Let's go. Okay. So the idea is to construct the object, yes, and count number of ways to construct the object. Okay. So how I construct it? I construct it by adding segments from left to right. Yeah. So every time I have already some picked segments. So I will pick another segments which do not intersect. Yes. And before I pick this, I also add some segments which I skip. So segments which intersect this position. Yeah? And I just count how many possible ways to add these segments. So I go left to right. So I my current position. T is number of segments I picked. So I picked the next position. Next position is J. Yeah. So this is number of possible skippable segments. I can pick any subset of skippable segments. So number of ways to do it is just 2 power this. Yeah. Then I need to pick some segment with this right border. There are many of them. I need to pick at least one. Yeah. So number of ways to do it is 2 power number of these segments minus 1. So it's number of ways to pick some non-empty subset of these segments. Yeah. It's j minus 1 because you need to pick left border. Left border should be somewhere here, just j minus 1. Yeah. Left border should be anywhere in this segment. And that's it. So we calculate number of skippable segments, number of segments we need to pick, and just make transition. So I make number of ways to get to this state multiplied by number of ways to make transition. Yeah. So I make transition from I to j in this number of ways. That's it. And that's just dynamic programming. Graph contest. Okay, maybe also yes. Graph is just too wide topic. I don't know. So there need to be some specific. Make some DFS temp contest or BFS temp contest. It's not that fun actually. I don't know any fun graph problems. Or there are some very there are some crazy ad hoc problems about graphs, but also not very fun. Okay, if you have any interesting ideas about problems, can you send them to me somewhere in direct messages? So I will try to combine something like this. Last problem. Let's go. Okay, I spent an hour solving this problem, mostly because of this last part. So this number is relatively easy to calculate. But then restoring this sequence is pain in the ass. So I spent too much time doing it. Maybe because I was just tired after all these previous problems, but okay, let's see. So the idea here. So we need to visit all the all the positions in sorted order. The problem is I have some equal elements. So equal elements you can visit in any order. So let's keep all the process into steps. Yeah. So you have this. You have not some number of zeros. So first you need to visit all the zeros. So you start somewhere and visit all of them. I don't know, like you go here, 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 here. Visit all the zeros. Or you can go, if you have, you can do it some strange way. So imagine you have some starting point. You imagine you started here, yeah, and you need to visit all the zeros. So you can do it. For example, let's remove this. So you can do it like you can go here and then go backwards, go here, yeah, and then you visit all the zeros. And now you need to visit all the ones. So you look at all the positions of all the ones. So you go to some first one, and then you need to visit all other ones. Yeah. So you can do it again, something like this. You go here, then backward, back. Yeah. So let's keep the process of visit on all the numbers into steps when you visit all equal elements. Yeah. Now, if you visit all equal elements, so imagine you have element x. So you need to visit all of them. So some of them will be first. Yeah. So let's pick first element. So imagine you started here. Now you need to visit all other elements. Some of them will be last. No, so let's say element I will be first and element J will be last. So I need to start here, finish here, and visit all these elements. So how you do it? No, there are two ways. You can either do it like this. Okay, let's write it better. So we go click, and then like this. Or you can do another direction. You can go this, and then go backwards here. So it's the same, just mirrored. Yeah. That's it. So again, now the trick is there are not that many pairs of first and last elements. So the constraints are kind of small. So I have 2000 elements. Yeah? So I can look at all pairs. First element of the sequence, last element of the sequence. For the first and last element, I know how to go from here to here. Yeah, you go there, or another direction. Okay, and after you take all element x, you need to move to element x plus 1. Yeah, so again, you have some element. You have some number of elements x and some number of elements x plus 1. Okay, no, not x plus 1, it's also this element y. Next element is y greater x. Next element. Yeah. So for each element x and each element y, you see how much time you need to go from here to here and calculate this parameter. Okay. Not clear enough. Okay, let's look at the example. Sorry, difficult problems, hard to explain actually. So what we have here, we have 0, 1, 2, 2, 2, 1, 0, 1, 1. Yeah. So how we visit them? We visit them like this. We visit 0, 0, then we visit 1, 1, 1, 1, then 2, 2, 2, like this. Yeah. First we visit 2 zeros, then 4 ones, then 3 twos. Yeah. So I split it all into segments like this. And I have these. So these points. Start of the segment, end of the segment. Yeah. So I need optimally go from here to here, then from here to here, then from here to here, and so on. then the number of states will be small. Yeah. So for every segment, number of states equal to number of elements of this type. So I have 4 states here, possible 3 states here. So total number of states will be n. You see? Not sure if it's clear enough. So what I will do for every element. So again, let's have some step. So imagine in this configuration you have some elements x, and there are like 5 of them. So on this cycle there are 5 x's. 1, 2, 3, 4, 5. Let's calculate 2 values for each of them. The minimal number of steps to start from this segment or from this element, and minimal number of steps to end in this segment. So here I'm in one of these 5 states. Yeah. So for each state, let's calculate d1 of I is just minimal number of steps to get to this position and start this segment. And then I will calculate d2 of I. It is minimal number of steps to get to this position when I end this segment. Yeah. So to do this, you need 2 types of transitions. You need to transition from the first element to the last element. That's just what I drew before. So you move from I to J. So if you started here and you finishes here, then you do something like this. You go in one direction, then you go all the way in opposite direction. So you know how much time do you need to go from position I to position J. Yes, if you fix both these positions. Yeah. And you need transition from X to the next element too. So if the next element is Y, but again, you can do it in n squared time. Yeah, you can take all possible positions of X, all possible positions of Y, and just calculate all possible transitions. That's it. That's basically. Okay, so this part of code which calculates the minimum is relatively easy. Let me show you. Let's debug. Okay, it's already code is already complicated because I have these parts for path restoration. But again, let's see. So I have these 2 values, d0 and d1. So d0 represents minimal time to start the segment, d1 is minimal time to end the segment. And I do it for every position. Yeah. So I need to start the segment in this position, or I need to end the segment in this position. Yeah. Going on. Find all positions. So I take the element. So B is B is just a sorted list of different elements. What question? Do you say something? Wait, do I hear you? Oh. Did you say something? No. Okay, I didn't get your question, but okay. Yes, it's 2,900 difficulty on cold forces. Pretty difficult problem. If you at least have some ideas about solving this problem, already good for you. So again, I pick some elements. So array B contains all the different elements in sorted order. I pick some element BT. Find all positions equal to BT. So this vector x contain all the positions I need to consider now. Yeah. Consider starting position. So if it is the first element, I just go from starting position S to this position I. Then here, okay, this looks scary. Okay, so this part calculates the movement from the start of the segment to the end of the segment. I move in one direction or in another direction. So let's look this part. Second part is the same symmetrical. So if I move from position I to position J, I first move in one direction this distance. This distance function, just helper function, calculate distances. Or distances on the cycle, not important. Yeah. So I move some direction, some number of steps in one direction, then some another number of steps in another direction. Yeah. And my distance will be this multiplied by 2 plus this. Yep. Okay. So this part is L, this part is R. Yeah. So it's L multiplied by 2 plus R. So it's total number of steps from start of the segment to end of the segment. If I start here in position I and end in position J. So if I start in position I and end segment in position J, then I need this number of steps. Yeah. So my total number of steps will be d0 of the starting position plus number of steps this. Yeah. And for this final position, I update dynamic programming. Okay, this code was much easier before I added all this path restoration step, but doesn't matter. Okay. So this part is the same but symmetrical. Yes. I just go in other direction. So okay, same thing. And here I move from my number to the next segment. Yeah. So I say if my segment is not the last one, I take the next segment t plus 1, find all positions which contain the next element, yes, and move from my element to this element. And again, I consider two cases when I move in one direction or in another direction. Yes. So I update d0 using d1. You see? d1 is end of the segment. Yes. I move from my end to the next beginning. Yes. See? With this distance. Just moving. Yes, in the end, just calculate the minimum. Yeah. And here finally I have path restoration. So all this other code is just for path restoration because it's okay. I don't know how to do it easier. The problem is when I do these steps, I kind of forget. So you need to output all the elements you visit, and I kind of forget which elements I visit. So what I do, I simply I remember which big steps I perform, yeah, and then just simulate all these steps. Yeah. So what's normal way? How do you restore the path? Yeah. So you kind of for each state of your dynamic program, you restore how you get to this state. So you restore the previous state. So you in the end you go from the end, you go to the beginning, backwards, yes, and restore the path. That's how we normally do it, yeah? Yeah, so here, yeah. So I restored by using, so array P is not needed anymore, actually. Okay, I will keep it, okay. So this array E tells you how you get to this state. So I move from my state I to the state J by performing these operations. Yes, I move left in one direction, left another direction, right on. And I do it in reverse because I want to reverse it in the end, doesn't matter. Yeah. So you build reversed path, so you do everything in reverse. Scary looking code. So again, so this thing tells you how you move from one state to another state. Yeah. Then in the end, I will combine all these sequences into one big sequence here. Where is it? Where is it? Where is it? Yeah, here. So I go from the last state, move backwards. Yeah. And every time I look at all these operations from array A1, array A0, and combine all these operations into this large array R. So this array R is contains information of how I moved in big steps. Yeah. So I don't want to make plus minus one. I make plus minus many. Yeah. These big steps. Now, during these big steps, I need to visit everything which I can. Yeah. So later I just, so here, I hate this problem so much. So here I just simulate this. So I take all these moves and just simulate these moves. So I can move, so while it's on zero, so if I move in the positive direction, move in the positive direction. If I move in negative, move in the negative direction. If I see the element which I need to visit, I stop, add this current difference to the answer, remove this element, and reset the current shift. Maybe it can be done much easier. I don't know. So again, the whole difficulty problem is this path restoration. Without path restoration, it's much easier problem actually. Let's look at actually. Tutorial. Let's look at the author solution actually. I'm interested. Maybe I missed something. Okay, 200 lines of code here. Okay, mine is even shorter than the author solution. Okay, so it's what kind of what's supposed to do in this problem, right? So it's supposed to be tricky implementational problem. Okay. Okay, sorry for that. I didn't expect this problem to be that difficult actually. So again, it's just not very difficult. So idea of the problem is not that difficult, but all these implementation details can make it overcomplicated. But again, if you even try to approach it, good for you. So thank you again for joining me today. See you in 2 weeks.